chemical bonding. Does a change in mass occur during a chemical reaction? The answer is given by law of conservation of mass. No detectable change in the mass occurs during a chemical reaction. If the total mass involved in a chemical reaction is precisely measured before and after the reaction, there is no difference. This law was actually put forward by Antoine Lavoisier in 1774, who is called the father of chemistry. When a candle is burned in an airtight container with oxygen, there is no detectable change in the candle's mass, as illustrated by the balances pointer being in the same place before and after the reaction. Here is an example for law of conservation of mass. The complete burning in oxygen of 4.09 grams of carbon produces 15 grams of carbon dioxide. How many grams of oxygen is reacted? So we know that in a law of conservation of mass, the total mass on the left side and the right side of the equation is going to be pretty much the same. So if 15 grams of carbon dioxide is liberated, and what's the amount of oxygen that would react with 4.09 grams of carbon? So if you want to figure that out, then we have to subtract 4.09 grams of carbon from the original 15 grams of carbon dioxide, which is going to give 10.91 grams of oxygen. Okay, so I think we have already talked about the atomic mass of an element. Where do we find the atomic mass of an element? It's from the periodic table. So it is the atomic mass of an element is the average mass of all its naturally occurring isotopes, and this number is usually rounded off to the nearest 0.1 unit. So how do we calculate the formula mass of any compound? If we want to find the formula mass of any compound, then we needed to know the individual masses of all the different elements that make up the molecule. Okay. So here is an example. If you want to find the formula mass of methane, which has the formula CH4, then you have to take the individual atomic masses of carbon and the atomic masses of all the hydrogens, and then add them all together. So the atomic mass of carbon is 12 units, and for hydrogen it's 1 unit, and because there are 4 units, it's actually going to be equivalent to 4. And then you add everything together, 12 plus 4, that's going to be equivalent to 16 units. Okay. Here is another example for calculating the formula mass. Let's say that we wanted to find the formula mass of PbCrO4, which is lead chromate. For the atomic mass of lead is 207.2 units, and for chromium it's 52.0 units, and for oxygen we know that one oxygen is going to be 16, and there are 4 oxygens. That's going to give a total of 64 units, so that's going to be equivalent to 64 units. When you add all of this together, that's going to be equivalent to the formula mass, which is going to be equivalent to 323.2 units. Okay, now let's go on to law of definite proportions. Different samples of a pure compound always contain the same elements in the same proportion by mass. Okay, so to put it in a simple way, if I take water from here or from Antarctica, it's still going to have the formula H2O. Okay, suppose if you take 9 grams of water, it's going to have 8 grams of oxygen and 1 gram of hydrogen. Suppose if you double the amount, you will have 18 grams of water, and in which you will have 16 grams of oxygen and 2 grams of hydrogen. Suppose you double that amount, then you will get 32 grams of oxygen and 4 grams of hydrogen. So in all of this case, you can see that the ratio of oxygen is to hydrogen is 8:1. Okay, so this is law of definite proportions. Let's do an example here. Actually, this example is about calculating the mass percentage of an element in a compound. If you want to find the mass percentage of an element in a compound, first you needed to know the molecular formula of the compound, and next you needed to calculate the atomic mass of the compound. Okay, so let's say what's the mass percentage of hydrogen in water and what's the mass percentage of oxygen in water. Okay, so if you want to determine this, then you needed to first calculate the formula mass of water. Okay, so which we did in the previous example. So each hydrogen is going to be 1 and there are 2 hydrogens, so 2 times of 1 equals 2, and each oxygen is going to be 16. There is only one oxygen, so the formula mass of water is going to be 2 plus 16, that's going to be equivalent to 18. Now, to calculate the mass percentage of hydrogen in water, what you do is the total mass of hydrogen present in water. So that's going to be equivalent to 2, right? Because there are 2 hydrogens. And what's the total mass of water? It's actually equivalent to 18. And then you multiply this by 100 since you're calculating the percentage, which is going to give 11.1%. Okay, and you do exactly the same thing for oxygen. Here, the mass of oxygen in water is 16, and this is the formula weight of water times 100. That's going to be equivalent to 88.9%. So this is how we calculate the mass percentage of any element in a compound. Okay, let's do another example. What's the mass percentage of carbon in carbon dioxide and oxygen in carbon dioxide? Okay, so in order to figure that out, obviously you needed to calculate the formula mass of the compound, which is carbon dioxide. So here there is 1 carbon, so it's going to be equivalent to 12 units, and there are 2 oxygen. 1 oxygen is going to be equivalent to 16. Because there are 2 oxygens, it's going to be 2 times of 16, that's going to be equivalent to 32. So 32, that's going to be equivalent to 32 plus 12, which is going to be equivalent to 44 units. Okay, if you want to calculate the mass percentage of carbon in carbon dioxide, then you simply divide the total amount of carbon, which is actually 12, by 44. Okay, so 12 divided by 44 is equivalent to 27.3%, and 32 divided by 44 is going to be equivalent to 72.7%. So this is how we calculate the mass percentage of different elements in a compound. Another example, how do we calculate the mass percentage of different elements in Al2O3? So there are 2 different elements. One is Al and the other one is oxygen. Let's find the atomic or the formula mass of Al2O3. There are 2 aluminum. So each aluminum is going to give 27.0 units. That's going to be equivalent to 54 units. And each oxygen is going to be giving 16 units. That's going to be equivalent to 48 units. So that's brings to a total of 102.0 units. And if you want to calculate for aluminum, it's going to be 54 over 102.02 times 100, which is equivalent to 52.9%. And for oxygen, it's going to be 48 divided by 102.0, which is equivalent to, or times 100, which is equivalent to 47.1%. Okay, so according to law of definite proportions, when a compound is broken down, its elements are formed in definite proportion by mass. And similarly, when the compound is actually formed, the elements will combine in that same proportion by mass. Okay, so what are limiting and excess reactants? Suppose if you do a reaction, there are always some reactants which are going to be left behind in a reaction. And these reactants are called as excess reactant. Okay, and the reactants which will run out super fast, the chemical reactions, are called as the limiting reactant, and because they are limiting the amount of product that is obtained in the reaction, they are called as limiting reactant. So it is a limiting reactant that's going to decide how much of the product is obtained at the end. Okay, let's see an example here. here copper reacts with sulfur to give copper to sulfide. As you can see from here, 10 grams of copper reacts with 5.06 grams of sulfur to give 15 grams or 15.06 grams of copper sulfide. So if you look into this, when you add the total, add the amount, add the mass of copper and sulfur, it's actually equal to the mass of copper sulfide. Okay, let's go to the second reaction. Here you still have 10 grams of copper, but the amount of sulfur is going to be 7.06 grams. In reality, 10 grams of copper will only require 5.06 grams of sulfur. The remaining will be just left behind, and therefore sulfur is the excess reactant here, while copper is the limiting reactant. Okay, let's see another case. Here, 20.00 grams of copper reacts with 5.06 grams of sulfur. Here, you have large amount of copper, which will be left behind. And therefore, it is the sulfur which is going to determine how much of the product will be obtained. Okay, so this is the limiting reactant. This is the limiting reactant, and this is the excess reactant.